We're back. Let's now summarize the time dimension. So up to now, our discussion assumed that all data was equally interesting, right? Like yesterday's updates were of equal importance as today's updates. We were pretty much assuming we were pretty much handling sets and multisets, right? This is what count-min sketches were handling, multisets, and Bloom filters were handling sets. So if a set contains updates from last year, this is still relevant. That was the idea. The question now, is this always a good, is this always an acceptable strategy? And now we'll shift our discussion into the case of streams. So where do we have streams? We already discussed about streams in when we were discussing about Spark. Think of network monitoring, for example, where we think of network monitoring, for example, where we want to monitor on the network routers the packets that arrive in order to be able to detect denial of service attacks. Yet another example is Visa, the company, the credit card company, where it's important for them to be able to detect credit card fraud, right? So in both these cases, and also in sensors like for detecting fire in the forest, so in all these cases, it's really critical to be able to focus on the last updates, on the most recent updates that arrived. So taking network monitoring as an example, it really makes no difference if 1 year ago or if 2 years ago, one IP address sent one message or 1,000 messages or 1 million messages. Why doesn't it make any difference? Because of the way IP addresses are allocated, because of dynamic IP address allocation, DHCP, and so on and so forth. And also because maybe 1 year ago, this computer running over there was compromised, but now it's no longer compromised, and so on and so forth. So time for this and for other scenarios, especially for streams, time is very important. We want to be able to control our query range. We want to be able to query only on a particular time window, to restrict our query on a particular time window. We will discuss about 3 different models in terms of summarizing, in terms of managing time. The first one is the model that we have been using up to now, what we call the landmark model. The landmark model, the simplest of all, is from the time that I start monitoring, everything that arrives after this time has an equal importance. This is what we have been doing with the count-min sketches. This is what we have been doing with Bloom filters, right? So we were starting our monitoring, or we were starting our summarization, and then everything that came after that had an equal importance. The second model is a bit more complicated. It imposes or it introduces a decay of old items. It introduces diminishing of the importance of old items. And the third model, it clearly expires old items. So an item that moves out of a window, of a sliding window, becomes simply expired and gets removed. Let's see each of them. By the way, we'll now be doing a simplification. Remember, time is a different dimension than what we have been discussing earlier, the frequencies, for example, or the memberships of sets, right? So we have 2 different dimensions. The one has to do with the information contained in our set or in our stream, if we're summarizing a stream. And then we have this dimension of time, which is very relevant to streams. It's more relevant to streams. So as a simplification in our discussion, we will assume that we want to do basic counting on the binary stream. So we will forget for now that stream will come with values, will come, for example, with IP addresses like IP address 10.0.0.7, 10.0.0.8 are different IP addresses. For now, our input stream will simply be binary. Like it's either a 0, which means that something didn't happen, or a 1, which means that something happened. And what we want to succeed is simply count the number of ones that arrived. In terms of describing time, we will use two approaches. The first one is what we call the time-based window. For example, I want to see all updates since this particular time, or all updates in the last 1,000 seconds, 100 seconds. And then we also will talk about the event-based window, which doesn't correspond to real time. It corresponds to, let's say, the last 1,000 updates, the last 5 updates, and so on and so forth. Let's start with the landmark model. The landmark model, as I said already, is the simplest of all, is the easiest case. So it takes all parts of the stream it assumes that all parts of the stream after the query will be of equal importance. Let's see how it happens here. This is our current time. And then everything that arrives afterwards is assumed to be of equal importance. And the query that we want to execute is simply count the number of ones in this binary stream. In this case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that's a very easy query to answer, right? So we just need to maintain a counter that monotonically increases. We can provide an exact result just by updating this counter every time that we see N1. Yeah, the landmark model is a bit boring actually. It's just too easy for us. So there's another model that's a bit more interesting. It's called the decay model. And the idea with decay is that we again account the whole stream, but we decay the importance of older parts of the stream. So if we want to visualize it, here is how it looks. Let's say that the gray part here signifies the importance of each of the bits. So when I arrive here, the importance of here is already too much diminished, let's say, compared to the importance of the most recent items over here. On the other hand, when I will be here, the importance here will be much larger, and the importance here will basically be almost 0. And the importance here will be a bit larger than the importance over here, of this bit over here. Okay? Now, how this decay works really depends on what you define as a decay function yourself. We have the exponential decay. The exponential decay will decay the old items quite fast, quite aggressively. We also have the polynomial decay, which will decay them in a much slower rate. All of these are nice, and they are useful, and they are used. But what is the most, let's say, what is the best, what is the most interesting for us is what we call the sliding window model. And this is interesting because it's also used in networks a lot, in network monitoring. And it's actually the most generic model. So the sliding window model itself can simulate all other decaying or all other models that we might want to execute. The idea here is the following. We have a fixed size window that the user says from the beginning, for example, size W, which will slide with time. And this will, whatever falls inside that window, shows the important items that we should account for. All arrivals inside that window will be of equal weight. And the challenge, of course, is how can we maintain the count, the number of true bits, over this sliding window without actually storing the full data. Why is that a challenge? Because if we cannot store all this data, all these bits over here, we also cannot expire them, right? So we can always increase by 1 when we see a count, when we see an 1. But the question is, how do we find out that one item just expired and we need to reduce by 1? This is what we will show now. Two approaches. The first one, the simplest, is what we call the jumping windows. And then we'll talk about one sliding window structure. The jumping windows are called like that because they are doing some coarse-grained jumps. So they're just breaking. Remember how we discussed what we discussed about Spark streaming, which discretizes the input stream? This is similar idea. It discretizes the stream and it keeps statistics for each small bucket. On the other hand, the sliding windows are a bit more clever. Let's see how it works. Yeah, okay, this is what the sliding window looks like. This would be the area to monitor. Let's see how a jumping window works. We have the W, the value W, which is what the user will want us to monitor. Like the last 10 items, the last 1 billion items maybe, or 1 billion arrivals maybe. And then what we want to do is to partition this W to smaller sub-windows of length Z. Now, these sub-windows of length Z will determine essentially the granularity of our statistics. So, as an example, I'm taking W equals 6 and Z equals 3, which means that I will be partitioning each W into 2 sub-windows. Okay? Z should be a divisor of W. So, what would that mean is that after I fill a sub-window, every time I fill a sub-window, I maintain a count for it. Here I filled this sub-window, I maintain a count, 3 bits are set to true, and then this sub-window, another count, 1 bit is set to true. So now I can sum them up. These 2 sub-windows, at this time, these 2 sub-windows cover my window of type of size W. Okay? So the sum, the number of true bits in my window of size W is 3 plus 1 equals 4. Then I will read the next 3 elements, these ones. Okay? What is the count in these 3 elements? 2. So now my large window will jump by removing this count over here and by adding the new count that I just generated over here. So 3 plus 1, which made 4. Then I remove the expired bucket over here, the expired sub-window, and then I add the new one plus 2. So what statistics do I need to maintain now? I need to maintain statistics. I need to maintain the count per sub-window. And it's up to me to decide on the cost. How? If I have, let's say, memory for storing 10 integers, then I need to make 10 sub-windows. Okay? If I have storage, if I have RAM for maintaining 1000 integers, then I can maintain 1000 sub-windows, which will give me better results. Of course, this W in that case will not be 6, right? W can be in the order of millions or billions, in which case it becomes a bit challenging to save the whole stream. Okay? So how do we execute the query? How do we say at each point what is the count within our window? We just keep the count like that as we described here. What I argue here is that the maximum absolute error is Z. Pause a bit and think why this is the case. What is the worst error that can happen? And when that happens? The worst error that can happen is when you just have, for example, here you have an estimate 3, you have an estimate 1, and then let's say that the new items that arrive are 0, 0, 0. Instead of 1, 0, 1, they are 0, 0, 0. And you are just before here. So your previous estimate is 3 plus 1, but your current value is actually just this bit and until here. So your current value is 1 from here plus 1, and this is actually 0. So you have an estimate 4, and your current value is 2. Z, which is 3, is the maximum error. Can it be more than 3? No, it cannot be more than 3, because if it's more than 3, this means that this bucket is completed, which means that you can just discard this bucket over here, this counter over here, and add a new one. Okay? The space complexity is O of W, the size of your window, divided by Z. The update cost, it's very efficient, right? It's constant time. Okay? So, okay, we are done with jumping windows. We can bound the maximum error to Z. Error is relative to W, right? So if we have a sliding window that's very large, then this Z, and we don't have much memory, then this Z is also not going to be very large. The error is relative to W, but not to the actual answer. So in the cases that we have significant difference between the last update and the previous sub-window that's just going to expire, then we get large error. A problem also that jumping windows cannot satisfy is that frequently we do not know a priori the length of the sliding window. For example, one user might want to ask for the count in the last 10 arrivals. Another user might want to ask for the count in the last 1 million arrivals, and another in the last 1 billion arrivals. And then the question is, how do we manage that? And also important, how can we get a relative error? An error that is relative to the answer, which is going to be tighter. So there are a couple of algorithms for doing that. Today we'll talk about exponential histogram, which is, I would say, the simplest algorithm letting window. This brings us to exponential histograms. So what's the key concept here? Well, in the previous slides, we talked about jumping windows, where we decomposed the sliding window range into small equi-sized sub-windows. Now, we'll take the same sliding window range, but now we'll decompose it into non-overlapping packets of exponentially increasing sizes. And the idea is that the newest packets that we'll be creating, like packet 5, which is the very last packet, which corresponds to the last arrival over here. So the newest packets that we'll be creating will have a high resolution, will have very few, will have a very small size so that they are accurate. Whereas as we go back in time, like packet 4, packet 3, packet 2, packet 1, as we go back to see older or to have a look at the older packets, the packets become larger. What does this larger packets mean? It means that this packet 1, for example, will store more than 1 arrivals, but it will keep the arriving it will keep the time only for the starting arrival and only for the ending arrival. So this 8 here is the size of the packet. It's the number of true bits that this packet summarizes. But it doesn't keep the intermediary time. It doesn't keep the individual time for these 8 bits. It just keeps the starting time of the packet and the ending time of the packet, which is essentially the starting time of the next packet. Okay? So the idea now is that we are summarizing our stream, our true bits like that, and then instead of we're throwing away the stream, we're not storing the stream itself. We're just storing. Let me get my pen. We're just storing these summaries, these packets, and then we're using these packets, these summaries, in order to answer queries. What does each packet mean? Let's take this packet over here, for example. Sorry for the ugly shape. So this packet over here says that from the starting time of the packet until the ending time of the packet, which is also the starting time of the following packet, I have seen 8 true bits, 8 ones. The rest were 0. Okay? Similarly, packet 2 says that from the starting time of this packet, 10.0305, until 10.0307, I have seen 4 bits which were 1, which were true. And similar for packet 3, 4, and 5. Now, think a bit. Do we know anything about the internal distribution of the true bits and false bits on each of these packets? No. If we say that we just know essentially how many were the true bits, right? And that's it. That's the thing we know. So the thing now is the following. By forming larger packets, we reduce the data size that we need to keep, right? We reduce the information that we need to keep, but at the same time, we reduce the resolution of this information. So for this small packet of size 1 here, I know exactly when this true bit arrived. It arrived at the end of this packet when this packet was completed. The same for here. Now for this packet, I know that the last bit arrived here, and then there was another true bit that arrived somewhere within here. So I do have some uncertainty for packet 3. There is one bit that I don't know exactly when it arrived, between the starting time and the ending time of the packet. And then for this bucket of size 4, yeah, I know I have even more uncertainty, right? I know that there were 4 bits arriving in here, but I don't know exactly, for the 3 of them, I don't know exactly when, and so on and so forth. Now, my description up to now considered that the time measure that we want to use is the wall clock time, is the physical time that we all know. It might be the case that we're interested for the arrival time. Remember, I have shown earlier at the very first slides when we're discussing the time dimension, I have shown also the alternative definition of time, which has to do with the number of arrivals of the number of bits that we read up to now, the 0 bits and the 1 bits altogether. So all the things that I just discussed about about wall clock time, they also apply for arrival time, for event time. Like here is where our packet starts when zero items arrived, and it completes when 17 items arrived. Whereas, out of the 17 items, I had 8 items that were true, and then the remaining were false. Okay, and so on and so forth. How much is the cost of storing one packet? We need to keep the ending time of the packet, or the number of arrivals, like this one over here, the 17 over here. And we also need to keep the weight of each packet, the number of ones. So I will not go over the proof, but the space complexity of this sketch that you are seeing, of this representation that you are seeing here, is O of 1 over epsilon log squared W, where epsilon is the desired error probability. We'll see in a couple of slides how this can be achieved. Okay, so now we know how these buckets look like. Okay, let's now see how these buckets are constructed. This is the first part. Sorry, how do we query these buckets? And then let's see how these buckets can be constructed. Okay, and this brings us to the query execution part. So I constructed my exponential histogram, or actually I'm maintaining my exponential histogram. I am keeping that up to date with the new arrivals in the stream. And now I also want to find out what happened in the last, let's say, the last 30 arrivals. By the way, unlike the previous slide over here you see that we monitor both time and the number of arrivals. So for this slide, just to make our life a bit easier, I forget time and I only use number of arrivals. So now I am at arrival 35. This has been the last arrival. And as I said, my query is about the last 30 arrivals. So how many true bits arrived in the last 30 arrivals? How do I answer this query? I first need to find all the packets that are fully or partially contained in my query. I am at arrival 35 minus 30. This leads me to arrival 5, which is somewhere here. Now, what does that mean? What can we say about packet 5? Packet 5 is fully included in my query interval. The same for packet 4, 3, and 2. So what can we do now? We know that in packet 5, in the time for packet 5, we had one true arrival, one bit seen, one more here, two more here, and four more here. So we can already sum 1 plus 1 plus 2 plus 4. So we already have 8 bits for which we know for sure that were included in our query window. What can we say now about packet 1? Well, there are plenty of options now, right? There are plenty of choices now. One choice or one possibility would be that we had 7 true bits over here and only one true bit over here. Another possibility would be that we had just 2 true bits over here and 6 true bits at the end. And plenty of other possibilities as well. Do we know the internal distribution for packet 1? No. We know absolutely nothing. We only know that packet 1 summarizes 8 true bits. So our best guess now would be to say that 4 of them arrived within the query interval, so 4 of them arrived at this time, and the next 4, the other 4 arrived earlier. I don't care where this separating line is, even if it was here instead of here, or even if it was here, the approach would simply say, okay, I assume that the query includes half of this bucket, the last bucket, or half of the items that arrived, half of the true arrivals, half of the true bits that are contained in this last bucket. Okay? So we have 1 plus 1 plus 2 plus 4 plus 8 divided by 2. What's the maximum error that we can have if we do it like that? The maximum error, or the only error actually, comes from this very last bucket, right? Because this is the only bucket that introduces some uncertainty. And actually we know that the maximum absolute error in our answer will be the size of this bucket over 2. Why? Because the true value is something between 1 and the size of the bucket. So if I say the size of the bucket over 2, then the maximum difference between the true value and the estimated value is the size of the bucket over 2. Okay? And a cool thing is that by using a clever trick, this maximum absolute error can also be translated to a maximum relative error, which is to a value epsilon, which will be chosen by the user. So the user will say, I want all the answers to be at most, to have at most epsilon relative error. Okay? Now, the space complexity of this is going to be what we write here, what we saw earlier as well. Remember, W is the maximum sliding window query that we want to support. Is the maximum size of our sliding window. But of course, the user is also enabled to use, is also allowed to use for the query a smaller W value, a smaller value of sliding window. So for example, here we used 30, but we could also use, let's say, 20 or 10, anything that we would want during the query time. So this W merely says you cannot query for more than that, but you can query for anything below that value. Okay? Now, as I said, the cost quality guarantees are provided by 2 algorithmic invariants. And let's see how these invariants work, because this is where all the juice is, right? This is where all the clever part is. The first one, the first invariant says that the size of each bucket J divided by 2 times 1 plus the size of all the buckets that come after J, that come after J should be less than or equal to epsilon. Let's translate that with an example. Let's show that, illustrate that with an example. The size of this bucket divided by 2 times 1 plus the size of this bucket plus this bucket plus this bucket plus this bucket should be less than or equal to epsilon. Okay? And what I argue and what I want you to have a look at home is, if this is valid, then the maximum relative error of any of our estimates for any query that we want to run in this sliding window, for any sliding window length, the maximum relative error will always be less than or equal to epsilon. Okay? Check it out. Try to prove it at home. It's really, really easy. It's not, I mean, you can derive it from here and from the observation that we made here that the maximum absolute error is actually the size of the last packet over here that is partially included in my query window. Of the packet that is only partially included in my query window. Okay? So this is the first invariant. There's no need to maintain this invariant directly. Why? Because we have a trick. We maintain invariant 2 instead, which maintains indirectly invariant 1 that we introduced here, which means that invariant 2 guarantees this part. And at the same time, invariant 2 itself helps us to maintain this nice exponential histogram, which I made very ugly here because of my drawings, but yeah, it used to be nice, right? So let's see how invariant 2 works. Invariant 2 says that for every packet size other than the oldest, the most recent, other than the oldest packet, that is the least recent packet, there are at most k over 2 plus 1 and at least k divided by 2 packets of that size, where k equals 1 divided by epsilon. Now, for the oldest packet size, which is also going to be the largest, there are at most k divided by 2 plus 1 packets of that size. So what is the change here? For the oldest packet, this part is missing. For the oldest packet, only the upper bound is there. For all the other packets, we have an upper bound and a lower bound. And notice here that the difference between the two is just 1. Okay? Now, given this invariant, we can compute the total number of packets. We have at most so many packets per size, and we have at most so many different sizes. So if we multiply both of them, we get the memory requirements. Okay? Now, let's run invariant 2. This is what will help us to maintain this very nice, this very neat compact structure. Let's set epsilon equals to 0.5, which means k, which is equal to 1 over epsilon, equals, is actually equal to 2, which means that according to this invariant 2, we have at most 2 and at least 1 packet per size, except of the last packet, of the oldest packet, the largest packet. So, a new arrival is handled as follows. We are just constructing a new packet of size 1, and we are adding it to the right, which will be the most recent packet, right? And then we'll need to check invariant 2 only for packets of size 1. If invariant 2 is violated for these packets, then we merge the 2 oldest packets of this size to create a new packet of double the size. And then we need to repeat the check, not for the packets of size 1 anymore, not for the packets of size I, but for the packets of size 2. If the invariant fails also for packets of size 2, then we need to repeat the check for packets of size 4 and so on and so forth. Let's see an example. Let's say that at time 20, I have these 4 packets, or sorry, 1, 2, 3, 4, these 5 packets. So I have a packet of size 4, another packet of size 4, a packet of size 2, and 2 packets of size 1. So right now, what is the k? K equals 1 divided by epsilon, so k equals 2. So we can have at most 2 and at least 1 packet. So right now, I have at most 2 packets for every size and at least 1 packet for every size, so it's perfect. I am not violating invariant 2. Now let's say that at time 21, I had a new arrival. By the way, you noticed here that I do not show the time for each packet, so this is how we used to denote packets, right? The size of the packet and the startup time or the ending time, right? Right now I forget the starting and the ending time. I just show the size of the packet because it's of no interest for this discussion now. So we had these 5 packets at time 20, and then at time 21 I have 1 arrival. What happens? I will construct this new packet over here at the very right, and then I will need to check, am I satisfying invariant 2 now? Well, I have 3 packets of size 1. This is a problem because I could have at most 2 packets of size 1. What should I need to do? What should I do now? I take the 2 oldest packets of size 1, which are these 2, and then I merge them to construct a new packet of size 2. This is my new exponential histogram. Before I go on, I need to recheck invariant 2 now for the packets of size 2. Is invariant 2 valid for these packets? Yes, because I have at most 2 packets of size 2. So now I can stop and accept a new update. At time 25, I have a new update. How do I handle it? I add it to the right, new packet to the right. I check invariant 2 again. All good. I can continue. Time 26, new update. New packet to the right. What happened now? Invariant 2 is violated again, right? Here. I have 3 packets of size 1. So I take the 2 oldest ones and I merge them to create a new packet of size 2. Before I accept new updates, I need to make sure that I have satisfied invariant 2. Have I? No, because now I have 3 packets of size 2 and I should have at most 2. So what I do is I take the 2 oldest ones and I merge them again and I repeat the same recursively. So this is my final, let's call it my steady state, right? So now I satisfy invariant 2 and I can accept finally new update. So what you see here, this process of these recursive mergings is called a cascading update. So an update that propagates until the end of the exponential, that propagates at more depth, that propagates to the right, sorry, to the left of the exponential histogram, maybe even until the very end. Okay? So how many cascading updates can we have? We can have as many cascading updates as the number of sizes of the packets that we have in our exponential histogram. So if we have 4 different sizes of packets, like 1, 2, 4, 8, then the maximum number of cascading updates is going to be 4. If we have 20, then it's going to be 20, and so on and so forth. How many sizes do we have? That was in the previous slide, right? We have at most these many different sizes, which is logarithmic to the maximum size of the sliding window. We are done also with exponential histograms now. So let's think a bit what we covered in this last part of in this part of the course. We talked about sketches, right? So we started with our own sketch, bloom filters, different variants of bloom filters, cuckoo filters, count min sketches, and then also FM sketches, and then we moved to summarizing time. And then for summarizing time, we simplified the problem a bit and we said, okay, for now, assume that you only have a binary stream. And then you want to summarize this binary stream, these zeros and ones only, instead of, for example, IP addresses. So how can we combine the two? Well, they can actually be, these synopses can actually be combined together. For example, combine count min sketch with exponential histograms, or we can also combine them with other things like with hash maps, for example. Basically, we have many different requirements out there, and there are accordingly many different synopses. Right now, we barely scratched the surface. The synopses that I have shown you are not all. There are tens of them. I showed only the most important ones, and there's a lot of exciting work actually in synopses, and I am actively working on this topic. So if you are interested to do your thesis, for example, on that, talk to me. I have several topics related, for example, how to implement synopses in GPUs, or how to design new synopses to satisfy to answer different requirements and so on. But also one topic that's quite interesting is combining synopses together. For example, let's say that we want to count the number of packets that are sent by each IP address in the last 10 minutes and then enable relative error. What we could do is we could use the exponential histograms that I have shown earlier in the previous slide, and then use these exponential histograms as values in a hash map. Let's say now that the relative error is not important anymore. We can accept absolute error. Then we can combine exponential histograms with count min sketches. So think of count min sketches, think of this 2D matrix, and take each counter in the count min sketch, which is currently an integer, and replace this integer with an exponential histogram. What kind of queries can you answer if you do that? Forget the probabilities now, right? Forget the error. But if you do that, what kind of queries can you answer? The possibilities are quite interesting, right? You can answer all the queries that count min sketches were able to answer, but now over sliding windows. We can even combine different synopses to answer some queries, like if we have two streams, two sets, and we want to compute their similarity over the last 10 minutes. How can we do that? If we want to count the number of packets that are sent by each IP address in the last, let's say, 20 minutes, or if we want set containment queries for the arrivals in the last 30 minutes. So why am I going over these questions now? Why am I showing so many here? I would like you to get comfortable with these synopses that we discussed, not with all, of course, but with these that we discussed. I tend to use one question, I tend to have one question at the exam, which is similar to these combinations that I am describing here, for example, or this combination here. Like, I want to answer this query. Make a synopsis, design a synopsis. You don't need to do the probabilities, but design a synopsis that will answer this query, maybe by combining two different synopses, or by combining, in the first case, a hash table and a synopsis, and so on and so forth. Okay? So if you get comfortable with this synopsis, it's very easy to answer this type of queries. I will not ask you to repeat any theoretical analysis. I may ask you, for example, to tell me what is the kind of error that this new synopsis that you designed will give. Will it be an overestimation, an underestimation, an unexpected value? What will be? And then would it be would it be an absolute error? Would it be a relative error, and so on and so forth? And remember that the idea is not so much on only using the particular synopsis, but is on getting used to these algorithms, to these ideas, and then applying these ideas in your own algorithms. Other uses of this synopsis, other uses of these sketches. Think how these sketches can help, for example, for finding the frequent item. For keeping statistics in the database, for example, to enable better cost prediction for query plans. We actually mentioned that already. It's for the join size estimation, right? For distributed stream monitoring, we mentioned that pretty much as well. We mentioned it as an example. We showed, for example, how count-min sketches can be merged, right? Summarizing static data, stored data. Would it make sense to use synopsis for that? Why not? Yeah. So if you can take a huge data set of several terabytes, it doesn't need to be a stream, right? If you can take a huge data set of several terabytes and you can summarize it to a few megabytes, that's great. If you can answer queries over that data set, that's super great. How can you use synopsis to speed up multiplication of matrices? How can we use synopsis, for example, to compute entropy, variance? Maybe one of these correlation measures that could be possible, I don't know. One of these correlation measures that you are interested in. So the sketches and the synopsis are extremely versatile. You can use them in many different applications. With this, I would like to conclude our discussion on synopsis. It was a quite extended discussion. We covered 3 lectures essentially with these videos, material of 3 lectures. We discussed about the data facet, and we went over a set of synopses there, conventional synopses like histograms, and we also briefly discussed about samples. We designed our own sketch, which I hope you enjoyed. It's, for me at least, it's much helpful to try to build something instead of just read how the other people did it. Then we discussed about Bloom filters, different versions of Bloom filters, count-min sketches and FM sketches. We showed also how we can utilize count-min sketches to compute range queries, inner product queries. Now this utilization, these techniques, these tricks that we have used for count-min sketches are by themselves already quite interesting, and then can be applied in other domains as well, and with other synopses as well. For example, think how we could apply, how we could combine this technique of dyadic intervals with Bloom filters. There are plenty of options, right? And then we talked about the time facet as well. The idea with the time facet is how can we summarize, or how can we take a stream? The time facet is more related to data streams, right? So how can we take a stream and then summarize the different parts of the stream in a different way? So in different resolution, and then still enable quality guarantees for the queries. We discussed 3 different time models: landmark, decay, and sliding windows. In terms of sliding windows, we had a look at the jumping windows and the true sliding window algorithms. And then we showed one of these algorithms, which is the exponential histograms. And this is how we concluded our discussion. Now, in terms of homework or in terms of reading, these papers, so the first one is a very, very interesting survey about Bloom filters. The second is the discussion for Kahneman sketches. And the third is about exponential histogram. These are really the key papers that you should have a look at. Now, most of the material included in these papers is already discussed in our discussion in these videos. But still, I would really suggest you to have a look at these papers because they are interesting. We didn't fully go over all of them, and they're quite interesting. They're quite educational.